Okay, so the function and made nothing about from dots, and so whatever formula is behind it is irrelevant because the next step we are not doing any differentiation. We are doing whatever we can do without actually invoking limits. So that's what you can, how far you can get without the limits. You take the difference quotient, so that's the formula right here. So even though I put here derivative, but really it's not. Look at it. So what is it? It's slightly complicated, but once again, you divide the two previous one by the by h over there. By the way, there's a tricky part I did here is that when you distribute the intervals non-uniformly, that's what's so special about this picture is that these intervals are changing. So it's all possible to do. They don't have to be necessarily the same. And now, so we're moving on to integrals, and what's the integration is this one. In the opposite direction. Even if you can think about, well, what about those bars? Why they vertical bar? Why horizontal bars?
They're differences, right?
No. It's a choice entirely. The choice of me which chart to use in Excel. So why did I choose dots here and bars there?
To distinguish the fact that one.
To distinguish, yes. Yes, they are kind of different ones. And probably one way to explain is that this is our location as a function of time. And how do we understand its derivative? We approximately as if we assume that over each of the intervals of time, the derivative, the velocity was constant. And that's what produces this picture. Okay? Another explanation is, well, let me try if I can do this. That's where we're heading right now. Change the chart type. I'm not sure this problem is going to work. Okay, did I make my point? So it's not really bars as much is not as much as these horizontal lines as much as they are bars. Those rectangles from end of calculus 1, this is, what do we call this?
A partition.
No, the partition is here, it's the Riemann sum on top of the partition. So partition of the interval, it just got stretched, but that's what we're roughly talking about here. Okay, so that's where we're heading, and I want to carry out this plan from scratch so that we can proceed smoothly into calculus 3. But I want to start with pretty much nothing, and just as if we're doing something, as if we are doing calculus 1. Okay, so what I'm going to be doing, and I want to compute I want to investigate a circle. Okay, so I'm going to plot the circle first, and then we'll see what we can do with it. Okay, so I'll put. Okay, so a circle. Okay, so a circle given by, or what's the equation? If I want to study the circle, what's the equation of the circle?
R squared equals x squared plus
right. That is a very good point. Unfortunately, it is the implicit equations. Every time, just try to plot this circle as you set it as the definition of the pretty much almost the definition of the circle. Try to do it numerically, and it is pretty much useless because you have to verify. Suppose you want to plot it. What's going to happen is you have to go along the whole square of pixels and verify every single pixel whether or not it satisfies this equation. So it not only takes so long, but also it is never exactly equal to say x squared plus y squared is never exactly equal to 1. So you'll have to take some kind of error, an allowable error, and so you will have, if that error is small enough, if it's too small, then you'll have nothing. If it's too large, you'll have everything. Okay. If it is in the between, you're not going to have a nice curve ever. You're going to have a bunch of points creating like a circular ring. So that's what implicit equations do. They're very, very inconvenient. That's why we switch to functions because then I will be plotting in x's and y's will be my outcome. So for example, let's say start here, and I'm going to put x's here in this column, starting with -1, because I'm looking at circle of -1, and then I will be making a step. What is the length of this step? Well, let me actually put more stuff here. I'm going to be, the equation is actually, that is explicit. The explicit equation is y is square root of 1 minus x squared. So that's what I'm going to be looking at. I'm going to plot it, and then we'll look at what kind of, what we can do with it. Okay, so, specifically x will be between -1 and 1. Okay, and then we're doing numerically, so we'll have to divide this into smaller subintervals. Remember what we just saw a minute ago? This one, those little intervals over there, and these. So let's do the subdivision. This is how I'm gonna have. I'll put here my interval here, -1, 1. Okay, and then over here I'll put my, say, n equal, how about 10. Okay, so n subintervals. The Riemann sum, eventually we're going to end up with the Riemann sum of n subintervals. Okay, so then I have to divide my interval from -1 to 1 into 10, and to compute what? Compute my h, which we already have seen, the increment of the independent variable. Okay, so how do I do it? I just take I'll take equal the upper limit, parenthesis, the upper limit minus the lower limit, parenthesis, divided by the number of intervals. Okay, so it gives me 0.2. Okay, and now I will going along the column of x, making a step of 0.1. So this one is actually equal to the lower limit. This one. Okay, so and then I progress by 0.2. So it's equal to the previous one plus 0.2. So it will be R4C2. Okay. And then, so I can have as many as I like. At some point it will break down because the function is what did I do? I have no idea what I did. That's, okay, sorry. Okay, so as you can see, it goes on one step at a time, but once we start computing y's according to that formula, so I'll put here simply, that's the inputs in the x's, outputs y's, so it's equal to square root of 1 minus this volume, squared. I need parentheses. And one more over here. Okay. Okay, so x is -1, y is 0. Okay, so if we spread it down, we'll see that things don't work out entirely because beyond some point, beyond 1, y's become negative, and so the function doesn't work. Okay, so and the square root will be undefined. Okay, so I can plot it. Let me plot it. Okay, x's and y's. Insert chart. So I could insert. Let me insert the line. That's not it. This one. No, again. Okay, so sometimes it's just not thinking. Okay, so let's select data. Select data. So I'll be just choosing the range for this one. I'll just choose this. Okay, so that's my circle, if it looks like a circle, but because only 10 points, so it certainly doesn't look very accurate. But now, what we're after, we want to compute this area. Okay, if we want to compute this area, well, first of all, I could do what I just did last time, and that is actually probably makes sense to switch the type of data, the type of chart, so that we can clearly see the Riemann sums. It is a Riemann sum with 10 intervals, starting at 0, ending up with 0 as well over there. Okay, so they are certainly not y, but actually, well, let me try to quickly check. There is a... Doesn't matter. Okay, so this is simultaneously the graph of my function, and it is the representation of the Riemann sums. Incidentally, I could do a better job because I put 20 here. Well, so the picture becomes certainly a little better. Okay. Okay, so now I want to produce Riemann sum and compute it, and compute the sum of these. So I have to be careful with what I do because, well, that's what we're looking here is that y's are the heights. These are the heights right here, the heights of those bars. So where the width, remember that's the Riemann sum, what we do it with, we multiply the width by the height and then add them together into and that's the Riemann sum. Okay, so I need also the width, and that's why I left here a column. And that's the column widths. What are they? They simply, they will all have the exact same width as delta H over there, but I still do it anyway in this fashion. So I subtract the previous one from the last one. So I'll be subtracting this equal this minus that. Okay, and on. So these are the widths, and they are all the same, fine. Well, the point of this is just computationally more convenient, and I do want to list it here. And secondly, remember that the widths do not have to be equal; they could vary. Okay, so then we have a sample functions, which gives me the heights of the bars, and then we have widths as well. So all we have to do now is just multiply this by that and add together. Okay, so there is a special function for that. Let me put maybe the answer here. So my Riemann sum is equal to, and I'll put it here. Okay, so I exclude this one. Okay, so it's called sum product. Okay, sum product. Okay, so two arrays. The first array will be the ones for the widths, and the second array is the for the heights. Okay, that's all. Okay, so okay, so what is the meaning of this number?
The sum of the area of the rectangles.
Okay, which is yes, which approximates
the area under the curve,
which is equal to
the
what?
Antiderivative.
No, the area under this curve, under this particular curve.
Pi over 2.
Pi over 2. Right. So this is pi over 2. Let's verify that this is actually, we are anywhere close. So this is equal to, so I'm writing next to it, over 2. Okay, so that's the difference. So the actual pi over 2 is 1.57, and we got 1.55. So that's pretty close. Okay, so that's calculus 1. Okay, so now what do we do if we wanna do calculus 3? So what would we do with this?
Same idea, just instead of a curve, we'd have a surface, and instead of an interval, we'd have a rectangle.
Yes, exactly right. But I once again I want to continue with this part. I don't want to do it from scratch. Let let me make a copy of this, and then, so instead of computing the area of a circle, what am I going to be doing?
Volume under the surface.
Which is, here's the word for it.
Oh, the volume under the surface?
Yeah, no, what I meant is what is the surface?
Cylinder?
No,
Sphere.
sphere, the sphere.
Down,
So,
yeah.
so the sphere will be computing the volume of the sphere. Okay, so, now specifically what is going to happen? So this chart probably won't be useful, nor the heights will be useful because this is still a function of two variables. So we have to introduce the second variable. Do you remember how we do it? The second variable where we put it? In the other direction, right? So we chose this is the variable, by the way, and I chose the variable to be located x variable vertically, and now we have y variable which will be horizontal. We just have to put them together in a nice way. So let me see. So my function will be so my function will start over there. Right here, so I think, no wait a minute. So I'll need two columns, so the two rows. This will be for the widths again, and the next one will be, and this will be for y, I think. The row for y's. So that picture doesn't work anymore, but think about, and plotting is not going to work anyway. Try to look from above. So y will be running between -1 and 1 again. So I'm not going to do that any different here. So I will simply starting point of y's will be still this one, -1. This one. Okay, and then I proceed to the right in the same fashion as before, adding h one at a time. So these are y's is equal to the previous one plus this one, which is row 4 again, row 4C3. No, C2. Okay, and then I have a bunch of y's that way. A bunch of y's as necessary, as many as necessary. Okay, so I guess I don't have quite enough room to have them all. Okay, well that's okay. Okay, now here we're going to be computing. If I did it right, I'm going to be computing in this rectangle. Let me kill this for now. Okay, in this area, this is where the values of my function will be located. So once again, these are x's, these are y's. The formulas, this is one of the simplest, the formula that we started with, but it has only one variable. So what is the formula for the sphere?
Z equals
Yeah,
minus y squared inside the.
minus y squared. Okay, x and y between -1 and 1. Okay, so this is the formula we're gonna implement. Okay, so that's I correct. It's already it doesn't take a lot. I'll just then I subtracted x, same row, column to back, and here I will be subtracting. Why do I have a parenthesis here? There's absolutely no need for it. On this one, parenthesis. I don't know why I put there. There's no need for it. And here I am subtracting this one. Same column, 3 back. Why is it 3 back? I think I have an extra row there. Okay, so there we go. Well, that graph doesn't matter anymore anyway. So let me kill it. Okay, so let's do numerics. So this is my function. I'll just spread it out as much as necessary. And what did I do wrong? I don't think my formula is correct. 1 minus, oh, so I forgot squared over here. Squared. Okay, so we're doing it again. Why it didn't work out? Well, because we are at the point negative 1, 1, and what's wrong with negative 1, 1? It is, there is no, the function is undefined. I did something wrong again. Oh, I see. Okay, so that was wrong. Okay, so let me fix the formula. So same row, no, column. I have to specify the column, which is 4. Okay. Column 3. And row over here is 4. Okay, so the reference has to be, as you can see, this is to confirm. Okay, so let me show you. Okay, so this. Okay, we'll write it down. What did I do? What did I do wrong again? So 1 minus same row, 3rd column. Same column, row, 4th row. Okay, so everything seems okay to me. Why isn't it working? I don't know why it just didn't copy. Okay, that makes more sense. Okay, you see what we're getting here? You see how what's in the middle? Probably I could do a better job like this. If I just change the column width to some more reasonable number, let's see, 5 maybe. Okay. So what are we seeing here?
Values outside the domain.
That's right. So wherever you have those crosses or hashtags, it is where the numbers lie. So the domain in the most literal sense. The domain is where the function is defined, values of x and y, and outside of this, which is a circle, well, believe me or not, this is a circle, and outside of this circle, 1 by 1 on the xy plane, the function is undefined. Okay? So there we go. And otherwise, see, in the middle it reaches 1. Otherwise, it is a surface, and I could plot it, no trouble, I think. So if I go and try to insert, where are those? Where are the surfaces? There's a surface here. Okay, so here it is. So Excel thinks of these areas where the functions are defined as zeros, and so you're not getting a circle sphere, but rather a part of the sphere with the flat area at the beginning. Okay, so but let me take this maybe prettier. Okay, so that's my sphere. And now to compute the volume, what do? I have to compute these. I'm not sure Excel allows me to do that, but I could simply try to add these. So okay, tell me how do I, from this data, how do I compute the area of the volume? So these are the heights. These are the heights of the bars, which you don't see here, but they are underneath the sphere. And we have a bunch of them, so it should be true inaccurate if we just know what to do. So what do we do?
Since we've used I forget that, it's called a regular partition. Since our partitioning is the same, we just consider the area of each of the little squares and then we multiply it by each of the functional values, and then we sum them all, right?
So it will be sum of, if we think in terms of regular Riemann sum, which is what we are getting to in dimension 2, it will be multiplication of the to find the volume of something of what? Not a bar, a flat one that we have seen previously, right? So that's what we saw previously, bars, literally, and we found the area of the bar was the height times the width. Now, these bars are three-dimensional now, right? We don't see them, but that's what it is. Underneath the surface is and above each of these cells, imagine like they are sticking out like this way. Okay, so they have width and depth. So with the depth and the height, depth, width, and the height, you have to multiply them all three. The heights are in this table, but the width and the depth, unfortunately, they're the same. They're almost equal to 0.1. So if I just, instead of doing it one by one, as I did with the last example, I don't have this luxury here, I don't think. So I will just simply, I just add these together, and then what? If I add these together, then what do I do with it?
You have to multiply it by 2 because it's only
By
half
2?
the
Why
square.
by 2?
Because it's only half. the
Ah,
square.
half, okay, what else? How do I take into account the width and depth of those
You
bars?
then multiply by the intervals.
Yeah, twice. So by 0.1 and by 0.1, right? Okay. So okay, let me do that. Okay, so I'll have to do, I'll say over here, I write, so my Riemann sum, this time I'll have a new Riemann sum over here. And what is its meaning? It is, I will simply put the sum here, sum of what? Of this whole array, and I just hope that it will be able to ignore the undefined business, hopefully. Okay, and then I multiply by 0.01, the area of the cross section of those bars. Okay, so I guess it does not. So it does the sum, but unfortunately, it just is unable to exclude these values. It still tries to add them, and since they are undefined, it thinks that this whole thing is undefined. So let me try to go a way that is kind of silly, but I'll just have to erase them and one by one, and hope for the best. And hope that it will work out. In the meantime, what is the answer? What is the answer we're hoping for? If you remember the answer.
Just take half, wouldn't it be 8/3 pi cubed?
8/3 pi, right. So I forgot to multiply by 2 as it was suggested. But, okay, let me try. So I'm killing this. And 8/3 pi, yeah, so let me, there's probably an option in Excel. Okay, 2.08, does it make any sense? Okay, so this was 8/3, 8 times pi over 3, right? 8/3 pi is the volume, half of the half, and that makes sense. Okay, so 8 pi, no wait a minute, pi r squared. No, pi r squared over 3, why is it 8? It's not 8, it's over 6, right? Pi over 6.
That should be 2/3 pi, right?
That's right.
Yeah, 4/3, I think.
4, yeah.
Oh, it is 4/3, so 4 over 6. Okay, over 6. Okay, so that should be closer. Okay, excellent. Okay, so it worked out, as you can see. So our approximation is pretty within one hundredth of the truth. So we computed the area of this, the volume of this hemisphere, and it is pretty close to the truth. So okay, so we're gonna just continue on with this, but let's next time hopefully this thing works, and we'll do the theory.